Section 4.2 is one-to-one functions and inverse functions. Remember at the end of 4.1, I told you that when you compose a function with another function and you get out what you put in, we said those two functions are inverses of each other, right? Here's the definition of a one-to-one function. It says a function is one-to-one if any two different inputs in the domain correspond to two different outputs in the range. The reason I'm talking about one-to-one after talking about inverses is we have a theorem that says if any function is invertible, it's one-to-one. And if it's one-to-one, the inverse exists. So these two concepts are closely linked. Basically what that means is for each x, there's only one y, and for each y, there's only one x. Back in college algebra or high school algebra, when you were learning the definition of a function, you learned that in order for a graph to represent a function, it had to pass something that was called the vertical line test. If we have a graph and we have a curve here that does something like this, this would not represent a function because here's a value for x that would be mapped to 1, 2, 3 different values of y. So this would represent something that's not a function because here's a value of x that's paired to two different values of y. It would fail the vertical line test. This is not a one-to-one function because here's two values of x that go to the same y. One-to-one means that it's just like it sounds, 1x, 1y, that's all there is. It's easy then to spot if a function is one-to-one because if you have two lines going to the same number or two lines coming from the same number, it's not one-to-one. So here, this graphical representation would represent something that is not one-to-one. It's a little harder to spot with points or ordered pairs, but basically if any of the x's repeat, it's not one-to-one. If any of the y's repeat, it's not one-to-one. So would B represent something that is one-to-one? Yes, it would. This is one-to-one. The way you can tell if you have a graph, this we said is a function, but it's not one-to-one because it fails what's called the horizontal line test. Because if I draw a horizontal line, and I have 2 points there, that means that there's a value of y that's mapped to two different values of x. So we would have something that's not a function. So here's the horizontal line test. If every horizontal line intersects the graph of a function and at most 1 point, then we say the function is one-to-one. So let's use a horizontal line test then to determine whether or not this function is one-to-one. Think about the graph of a quadratic function. If you can't think about it, let's draw it. Would this be a one-to-one function? No, it would not, because it would fail the horizontal line test. Here's a graph of a cubic function, basic cubic function, something like this. Would this be one-to-one? Yes, this would, because it passes not only a vertical line test, but it also passes a horizontal line test. So this one's a yes, this one is a no. What if I give you this? Would this be a one-to-one function? No, it's not even a function. It fails the vertical line test. Remember, in order to be a one-to-one function, first it has to be a function, which means you got to check the vertical line test first, then check for the horizontal line test. So suppose f is a one-to-one function, then for each x there's exactly one y in the range because f is a function, and to each y in the range of f there is exactly one x in the domain. The correspondence from the range of f back to the domain is called the inverse function. So here's an example problem. Let's let f of x be represented by this set of ordered pairs. We can represent a function using a graph, an equation, a table of values, or a set of ordered pairs. Find the following. Since my function is a list of ordered pairs, my inverse will also be a list of ordered pairs. It might help you if I told you this definition of an inverse function means that in order to get an inverse from a function, and this is the notation we're going to use, we switch x and y. That's why you have to have a one-to-one function in order for an inverse to exist. Like I said, this is the notation we have for inverse functions. In order for a graph to be a function, we say y is equal to f of x. To be an inverse function, we just put this -1 up here as in our notation. And you're going to see this when we hit the trig part of the course. We're going to use this -1 as an inverse function notation. This is red, y equals f inverse of x. Now, this is not a power. It's function notation. F inverse of x is not the same thing as 1 over f of x. This is not a negative exponent. It's an inverse function notation. And how we get the inverse function is we switch x and y. Knowing that now, here's your function f defined by this set of ordered pairs. How do we get f inverse? What is f inverse going to be? 1, negative 5, 3, negative 2, negative 2, 1, 6, 3, negative 5, 4. What is f of 3? This means go to your function f, and in place of x, you plug in 3 and see what the y is. What is f of 3? What is f inverse of 1? Negative 5. Because now you go to your inverse function, and in place of x, you plug in a 1, and you get back a negative 5. What is f composed with f inverse of negative 5? Well, let's use our embedded parentheses. This is f of f inverse of negative 5. What is f inverse of negative 5? We go over here to our inverse function, and in place of x, we plug in negative 5, and we get 4. So that's going to be f of 4. And what is f of 4? Negative 5. Well, that's cool. We put a negative 5 in, we get a negative 5 out. But at the end of 4.1, isn't that what I said was going to happen? When you compose a function with its inverse, you get out what you put in. We got out what we put in when we composed a function with its inverse. Let's look at E. F composed with f inverse of negative 2. Use the embedded parentheses notation. That's f of f inverse of negative 2. What is f inverse of negative 2? 1. F inverse of negative 2 is 1. F of negative 2 is 3, but I was looking for f inverse of negative 2, so I got to go to my inverse function, and when x is negative 2, y is 1. So now we're looking at f of 1, and what is f of 1? Negative 2. We got out what we put in. Let's use the embedded parentheses again. F inverse of f of 6. Can we just say, oh, well, that's equal to 6? You're going to get out what you put in, right? But there's a problem here. What is f of 6? No, f of 6 is not 3. This means you go to your f function. That's up here. And when x is 6, wait a minute, x is never 6 up there. This is not in the domain of f. Now, someone picked up on the fact that, oh, well, I switched f and f inverse. That's okay. Let's do another one. I could ask you, what is f inverse composed with f of 4? F inverse composed with f of 4. Well, that would be f inverse of f of 4. What's f of 4? Negative 5. So now I'm looking at f inverse of negative 5. And that's going to be 4. Notice I got out what I put in because I composed a function with its inverse. As long as what you plug in is in the domain of the function on the inside, this works. Where you have exceptions is if you try to plug in something that's not in the domain of the function on the inside. F inverse of f of x is equal to x, where x is in the domain of f. This part is important. F of f inverse of x is x, when x is in the domain of f inverse. You can switch the order of the composition so long as what you're plugging in is in the domain of the function that's on the inside. Here's an example problem. Let's find the inverse function if f is equal to the square root of x plus 3 minus 1. You remember what the square root function looks like, the graph of a square root function? Has that shape. That's the parent function here. It's been shifted, though, how? Down 1, left 3. So we're going to go down 1, and left 3, down 1, left 3 puts us right here. And so here's a few reference points. And we sketch the graph, and this is the graph of f of x. Well, now I got to graph the inverse function. Well, what did I do? I switched x and y. So if this point, negative 3, negative 1 is on the graph of the function, what has to be on the graph of the inverse function? Negative 1, negative 3. That point has to be there. Here's the point at negative 2, 0. Guess what point is on the graph of the inverse? Alright, well, let's come up with an equation because it may be easier to graph if I write an equation out. So here's f of x. We're going to start with f of x. But y is equal to f of x, so I'm going to replace that y there. And what do I do now? Switch x and y, because that's how you get an inverse from a function, is you switch x and y. So what I'm going to write is x equals square root of y plus 3 minus 1. And now I just solve for y. So in order to get the y by itself, I'm going to come along and I'm going to add 1 to both sides. And that's going to give me x plus 1 equals the square root of y plus 3. What's the next step towards solving for y? Square both sides. What you do to one side, you have to do to the other. You can do almost anything you want, so long as you do the same thing to both sides of the equation. So that's going to give me x plus 1 squared equals y plus 3. Now what? Subtract 3. And I end up with x plus 1 squared minus 3 equals y. So my last step in this process is going to be replace y with my inverse function notation. So what I have then for my inverse function is f inverse of x is this quadratic, x plus 1 squared minus 3. This is a quadratic function which we know has this shape, basically that U shape, but it's shifted how? To the left 1, down 3. So that's where this vertex is right here. It's to the left 1 and down 3. So when I sketch my curve in, I have this shape. Wait a minute. That doesn't pass the horizontal line test. Well, let's back up a minute and think about this. What is the domain of the function f? The domain of f goes from -3 to infinity. What about the range of f? That's going to go from, remember I'm looking at the blue function here, that goes from where to where? -1 to infinity. Oh, I got to put parentheses on my infinity. Well, when I switch x and y right here at this step, don't I swap the domain and the range? So do I want this to be my function over all real numbers? No, I'm going to graph this function on the interval from -1 to positive infinity, which means I don't want that half of the graph. Now this function is 1 to 1 on this restricted domain. How did I know that that was the domain that I wanted? Well, the domain of the function is the same as the range of the inverse, and the range of the function is the domain of the inverse. When you switch x and y, you flip-flop your domain and range. When I draw this graph in, what results is these two pictures right here that are symmetric along this line, y equals x. Now that's a cool thing to note. The graphs of f and f inverse end up being symmetric about y equals x because I switched the x's and y's and it caused the symmetry along that line. So that's how you can tell if all you have is a graph, that you have a graph of a function with its inverse. You'll be able to fold this paper in half, this graph in half, and have the two halves match up perfectly. Consequently, where these two graphs intersect, it's going to be where the y and the x values are the same. Knowing what I just told you now, can you graph the inverse of this function even though I didn't give you an equation? What would you do? Switch the points, right? So give me a point that's going to be on the graph of the inverse function. -1, -2, 0, -1, 1 and 2. And then to sketch in the inverse, we just connect the dot. And look what happened. You didn't even have to try for it just by switching the dot. You have symmetry about the line y equals x. If you were to fold this in half along that line, the blue and the red would match up. Now, what kind of functions are guaranteed to have an inverse? 1 to 1. There's a theorem that says a function is invertible if and only if it is 1 to 1. If and only if is a powerful statement. It's like buy one, get one free. That means if you know a function is 1 to 1 because you're looking at the graph, you know it has an inverse, even if you figure out what it is. It has it. Okay, if you know that a function's 1 to 1, you know it has an inverse. If you know it has an inverse, you get 1 to 1 for free. It's impossible for an invertible function to not be 1 to 1. So let's look at this last example here. It says find the inverse function for this function. We're going to find the inverse and check the result. How could we check to see if we found the inverse correctly? We could graph it and check the symmetry, or the easier way is to see if f composed with f inverse of x is equal to, and f inverse composed with f of x is equal to x again. That's how we check the result. But first we've got to find it. So we start with what we're given. Okay, we're going to start with f of x equals 2x plus 1 over x minus 1. By the way, this is in the domain of the function. So what do I know about the range of the inverse before I ever do anything else? This is for the domain. Do I know anything about the range of this function? Not yet. I do know that for the range of f inverse, y is not going to be equal to 1. In a minute, I'll be able to tell you more about the domain of f inverse. I'll tell you what x is not equal to. And it's going to be the same thing here for the y on the function, because we switch x and y. So I need to get this, I need a y in this problem first. Replace what? F of x with y. So that gives me y equals 2x plus 1 over x minus 1. We don't multiply yet. We want to switch x and y. Then we solve for y. So that's going to give us x equals 2y plus 1 over y minus 1. Now we solve for y. And in order to solve for y, we are going to multiply both sides by y. So we multiply both sides by y minus 1. So that's going to give us y minus 1 times x equals 2y plus 1 over y minus 1 times y minus 1. Then we see that these are going to cancel out. Now what do I do? We're going to distribute the x across there. So that's going to give us xy minus x equals 2y plus 1. Now our goal is to get one y in the problem. Right now there's two of them. So the next thing you want to do is move every term with a y in it to one side and every term without a y to the other side. So how do I do that? Add an x, subtract a 2y. So when I do that, what do I get? xy minus 2y equals x plus 1. Now what? Factor out a y, and that gives me x minus 2 and x plus 1. Now what? So that's going to give me, can I just write f inverse of x now? That's x plus 1 over x minus 2. What is the domain of f inverse? X cannot be what? X cannot be 2. That means that y down here for the range of the function will not be 2 as well. It ends up being a horizontal asymptote, but we knew that, right? Because we did that whole unit on rational functions. Isn't that cool, though? What you got for the x, when you switch x and y and find the inverse, the restriction on x became the restriction on y, vice versa. Summary. If a function f is 1 to 1, then it has an inverse function, and we write that using inverse function notation. Domain of f is the range of the inverse. Range of f is the domain of the inverse. To verify that functions are an inverses, I didn't verify, but I'm sure we did it right. To verify, we would compose a function with its inverse and see if we get out what we put in. And if we were to look at the graphs of an inverse, a function with its inverse, it would be symmetric with respect to the line y equals x.